Professor Rai, may I request you to start the function?
Sure. Good afternoon and welcome you all on behalf of the SNBNCBS National Center for Basic Sciences, Kolkata. Okay, today we are here to celebrate the National Science Day. As you know that every year on 28th February, we mark this day as a Science Day. This was the discovery of the Raman effect by Indian physicist Sir Chandrasekhar Venkat Raman on this particular day. It was done in 28 February 1928, and for that he was awarded the Nobel Prize in 1930. Normally in this day we have got a good outreach program at the center where we have different kind of lectures, debates, and the students from the different colleges and the schools visit the center for hands-on training and lectures. But unfortunately, due to the pandemic, we just have to organize a lecture this year. And this year, the theme of the National Science Day is that that science, technology, and innovation. As you know, this is the government of India has come with the new policy of the fifth policy, national policy of science, technology, and innovation. So, theme of this year is the future of science, technology, innovation, and its impact on education, skills, and work. And today we are very fortunate to have Professor Rohini Gatbolli from Indian Institute of Science and Science Bangalore as the distinguished speaker today. So Professor Gatbolli is there in participating in several policy meetings in the government of India as well as several mega projects. So welcome you all, and I will request Professor Shahadash Gupta, Professor Tanushree Shahadash Gupta, our Dean Academic Program, to introduce the speaker, please.
Thank you very much, Professor Rai, for this welcome address. So it's now my pleasant duty to introduce the speaker to you, which is, of course, she doesn't need much of the introduction, but as a tradition, we need to introduce the speaker. So we are very fortunate, as Professor Rai mentioned, to have a distinguished person like Professor Gatbolli with us today. I have the opportunity of knowing her rather closely, and she is the inspiration for many of us, especially the women scientists trying to pursue the career in science. In a way, she has been the torch bearer of us. Professor Rohini Gatbolli is a professor at the Center for High Energy Physics, Indian Institute of Science, Bangalore. She is a particle physicist, best known for her work at CERN, the European Organization for Nuclear Research. Her work on high energy photons formed the basis for next generation of particle colliders. Some of these we are going to hear in her talk, used to study the fabric and the composition of the universe. Her work on various aspects of standard model of particle physics has created a lot of excitement, which describes the properties and behavior of elementary particles of the universe. She is a fellow of all three Indian academies and also that of the World Academy of Sciences, that was. She received a Padma Shri Award for her contribution in science and technology in the year 2019. Very recently, she has been received the National Order of Merit Award of France by the French government, which is actually very prestigious because being a foreigner to receive this award, which is equivalent to our Padma Awards. She is today a part of the International Detector Advisory Group for the International Linear Collider at CERN, which monitors design and working of the detectors. Apart from her work in academics, Professor Gatbolli is also a much sought after communicator of science, often delivering talks to young students, scholars, and scientists on everything in physics. So that basically makes her completely, absolutely brilliant speaker for today's topic. She is also a supporter of women pursuing career in science, as I have also mentioned. Along with Ram Ramasamy, she has edited the book on Lilavati's daughter, a collection of biographical essays on women scientists from India. And here I had a small role in contributing a chapter. I feel proud about it. She is also the chairperson for the panel for Women in Science initiative of the Indian Academy of Sciences. We are all honored to welcome Professor Gatbolli as speaker of our National Science Day celebration. Professor Gatbolli, may I request you to deliver your lecture?
Thank you very much, Tanusri, for this very, how should I say, laudatory introduction. But just an introduction that I am one of your older colleagues, not necessarily wiser, would be enough. So it's a great pleasure to talk at the Science Day of your institute. Let me spend a few minutes to start sharing the screen, and then I will, if I can see my screen. Yeah, good. Till this happens, it's always for me excitement.
It came out. Yeah, we could see.
We got
Yeah,
it.
yeah.
Okay. So, because of the theme of this year's Science Day, I decided that given the focus on technology and what are the implications of technology for future, I thought I would talk about mega projects as how many of the mega projects are a meeting ground of fundamental science as well as cutting edge advanced technology. So that is my plan. And I'm really pleased to be speaking at the Science Day celebrations of the SNBNCBS Center for Basic Sciences, with which I have had actually connections since the beginning of this center. So, what will I do? I will begin initially giving some introductory remarks about setting out why I wanted to discuss this. Then, the idea here is that I would try to show you and talk a bit about the current mega projects that India is either involved in or embarking upon. And then I would take the example of particle physics to talk about two mega projects in particle physics, one which is resident at CERN, and one which is resident, which we hope will be resident in India. So for that, I will first try to set the stage about few facts about particle physics at present. It would also mean a little bit of a tour down the memory lane as to how did we arrive here, and then how and why the scales of discovery tools have changed from the beginning of this journey. And that actually will tell you why we need mega projects now for the investigations in particle physics. So I would try to make case or try to make people understand what is the need and how these mega projects, how advanced technology is an essential part of this of these mega projects. And then I would sort of very briefly talk about the questions, queries about nature that we have, which still need answers, and what devices are needed for that. And then I want to end with trying to tell you that these technology that is required in these mega projects are not just for this blue sky research. So in fact, there is a very synergetic existence of sometimes a technology being developed for the blue sky research, but then it goes and changes the common person's life completely. And sometimes technology, some blue sky research has to wait till the high profile technology is developed through another investigations and for completely pure scientific reasons on some other horizon. I would say that at present, India is engaged or preparing to engage, as I told you, on many mega projects. So what is in green are the mega projects in which we are involved already. What is in red is a kind of mega projects that we are hoping will start soon. And in this case, there is one mega project that I will talk about, which is the experiments at the Large Hadron Collider, LHC, at CERN. And these are about explorations at the heart of the matter. What are the laws of physics that are operative at the ultimate heart of the matter? And the other one is the Indian Neutrino Observatory, which are explorations in neutrino physics and astroparticle physics, which is which is sort of the land that the particle physicists would want to explore in the coming decades. And INO happens to be a mega project that we would like to have based in India. And LHC, of course, is based at CERN in Geneva. So this is the tunnel of the Large Hadron Collider. And India has participated in making magnets, for example, or the precision positioning systems for magnets which are used to steer the protons that go at the pipe center of these magnets. And then India was also involved, Indian experimentalists, in building this huge detector, mammoth detector. And you can see here at the center, I don't know how big the screen is, but here at the center is a human being. So that should tell you the size of this mammoth detector. And here, unfortunately, we don't have a human being, so I can't tell you. But if a human being was standing here, that person will come up to this height, so you can get the sense of the size of the tunnel and the size of the magnets. All right. Then there is this INO, Indian Neutrino Observatory, and the planned Indian Neutrino Observatory detector. And this detector here is planned. This is an artist's conception because we don't have the detector yet. We don't have the sanction for the laboratory yet. And for the last 10 years, this is being planned. People know exactly how to build it. And this detector is about a height of a 5-story building. And it will be actually the world's largest electromagnet. And this will be layers and layers of this particular detector called RPC. Whereas there will be an underground laboratory of the INO project. And that underground laboratory, in fact, will have many more astroparticle physics experiments. And in neutrino physics, this experiment will, in fact, or this detector will address some very fundamental questions in the context of neutrino physics. In astrophysics and astronomy, I'm sure you have heard of the Laser Interferometer Gravitational Observatory, LIGO India, and this will do, once it is established, gravitational wave observations and study the physics of high gravitational fields, including black holes. Money has been sanctioned for this, and construction is supposed to begin soon. And of course, in the red, there is Square Kilometer Array. This is called, it's a radio telescope, and this is the next step in radio astronomy beyond the giant meter wave radio telescope GMRT that we already have in India near Pune. So this is just one slide to show you this LIGO India, which has been approved by the government in 2016. The site has been acquired, and this would be a huge interferometer consisting of these two arms. And what will these two arms contain? These two arms will contain actually very complicated fire optics, and the kind of technology that would be required to do these experiments would be the squeeze light technology, improved mirror coating, then advanced optics and laser technology, or mitigation of noise in motion, because this is really a motion of the size of 10 to the minus 18 centimeters, that, or rather 18 meters, that you want to actually measure in these experiments. And this has already been achieved in LIGO in the US, and LIGO India is going to be a third arm of this trinity. It will form the trinity. And the data analysis and the source and detector modeling and the gravitational wave astronomy, that involves an entirely different level of data acquisition and analysis. So this is the technology that is going to be required. Then there is Square Kilometer Array. And these Square Kilometer Array are actually many, many antennas over an area of about 1 square kilometer. That's why it's called Square Kilometer Array. And the collecting area of this radio telescope would be 30 times that of the GMRT, which exists in India. and this will have 3,000 small sized antennas. And then the challenges will be in the electronics to optical fiber, data transport, also sophisticated signal processing, which is India's forte, high performance computing, and using AI and machine learning for data analysis and interpretation. So these are the three mega projects that are at present there. You would have already noticed what are the commonalities between these mega projects. All the projects address very fundamental questions about secrets of nature. All need cutting edge technology, and they have led to new developments in the same. All are huge projects. All need global participation, and no one group, no one institute, or no one country has either the intellectual or the monetary resources to do it alone. So today I want to take up the case of two of the mega projects in particle physics in detail, and I want to tell you why, what is the importance of these two mega projects, and what is the importance of India's participation in these mega projects. So, this is right at the left here. I have shown you the photograph of a very famous sculpture by famous sculptor called Rodin. And this sculpture is called the Thinker. And actually, I think this Thinker represents what the entire scientific community, the world around, works on. In fact, I would say that the question is to know what makes the world around us tick, or how does it work? What is the heart of the matter? How do things around us work? Are they all made up of some fundamental building blocks? And if they are there, if the answer is yes, how are those building blocks held together? In fact, these queries have been age old. They have been with us from the beginning. And in short, I can say that the question has been, what are the bricks and the mortar of the edifice of life? The question has remained the same through the ages, only the answers have changed. Our perception of what the parts are has changed as our understanding how the parts are put together has grown. And it will not be too far if I say that efforts to answer what are the bricks and mortar of the edifice of life, this particular question has actually, I would say, propelled the development of the science through the centuries. So if you and me were in a few hundred years or few 100 years before Christ or few hundred years after Christ, and then at that time the Greeks, for example, thought that everything was made up of four elements: earth, fire, wind, and water. That's why the origin of the word element for these four elements of nature. And the Indian sages actually thought that everything was made up not just of earth, fire, wind, and water, but also space. And that's why they call Akash. So whether you believe the Greek philosophers, whether you want to believe the Indian philosophers, these would have been the elements, as we call them, as we understand, as the basics of everything around us. This was just a hypothesis. This was just a philosophy. But from that philosophy and from those elements of the Greek or the old Indian sages' time, from the Panchamahabhutas, actually from the beginning of the 18th century and a little later, actually chemistry made a big progress. And I do not want to go through that whole progress, but our understanding about what are the fundamental building blocks kept on changing. And then the answer changed from being chemical elements to molecules, to atoms, to nuclei, to finally quarks and leptons. And today, the branch of science that answers the question, what are the fundamental building blocks of nature, is the elementary particle physics. And the accepted worldview is that the fundamental particles are quarks, the leptons, and the force carrier, which we call them gauge bosons, which are the photons, the WZ bosons, the gluons, and of course, the final piece of the puzzle, which was found now almost 10 years ago, 4th July 2012, at CERN in Geneva at the Large Hadron Collider. So the picture of particle physics and sort of provided right now the answer to the question what everything around us is made up of, and if there are fundamental building blocks, how are they put together. But this is not all. Particle physics not only provides us an answer to this question, but in principle, the laws of physics which govern the behavior of these elemental blocks allow us to predict behavior of all matter. I think I will skip this slide because I am going to be running out of time as I see now. So let's skip this slide. Nothing. I was going to say that in the initially people thought whether the answer will be that whether the onion, when you keep on peeling, will it, you will keep on peeling it. But now we feel that the structure of matter is more like this Russian doll, that you can't take out all pieces of matter. And indeed, we think that we have arrived at this answer. And basically, particle physics has been able to answer these two questions: what are the elementary constituents of matter and what holds them together? But to do that, they have through the centuries, last 125 years, the theoretical physicists have actually developed the mathematical framework to describe how these parts are put together to form matter, how do they interact with each other, and how can one predict the behavior under different conditions. Again, this is very well known. All of us these days know the list of the fundamental building blocks, which you can see in popular literature or even on Wikipedia. And I'm not going to spend time on that right now, not because it's not important, but because I want to talk about something else. But this is here just for the sake of completeness, to show you that particle physicists in the last 150 years have established the properties of these fundamental blocks very accurately. They have measured their masses, they have measured their electrical charge, and in fact, there are these quarks, there are these leptons, these are the gauge bosons, and of course, in 2012, we have found the Higgs boson, which is sitting here. All right. So now we begin with the sort of at the beginning by saying that now we have understood that these are the fundamental building blocks. Now, I want to give you some sense of the sizes of these fundamental objects. We all know that things are made up of molecules, molecules are made up of atoms, and we have an idea what the size of an atom is, roughly a few angstroms. So let us start with that. Okay. So if we look at it, 1 angstrom is roughly 10 to the minus 10 meters. So let me call size of the atom as unit 1. Okay. And when you are looking at things, and when your least count of your meter scale is only 1 angstrom, you would say that atom is the fundamental particle. But when you get a meter stick with a least count which is bigger than that, then you begin to see that the fundamental object is perhaps a nucleus, because I cannot resolve it further. But the nucleus is about 10,000 times smaller than an atom. Okay, and a neutron or a proton is another factor 10 smaller than a typical nucleus, and that is, it's 100,000 times smaller than an atom. And for the quarks and the leptons, in fact, we have right now, strictly speaking, only a limit on their sizes. And we know that if at all they have a size, the size is smaller than, they are smaller than 100,000 times smaller than an atom. But actually, that it is smaller, at the largest, it can be 10 to the minus 18 meters. By an accident, this 10 to the minus 18 meters happens to be the displacement that the LIGO experiment has actually measured. But in this case, you don't really actually measure these distances. In fact, what we believe as a particle physicist, if you ask me, I would tell you that quarks and leptons most likely are point-like, and their size is definitely smaller than 10 to the minus 18 meters, or smaller than 100,000 times smaller than an atom. And all this has happened because one has looked at experiments from high energy accelerators, as well as the development of the theoretical models. And here I have taken 1, then 10,000, then 100,000, then 100,000, 1,000 times. I want to give you a feel of subject object. What does it mean by 10 times smaller or 100 times smaller? So I'll begin by this is a series of photographs which are taken from a website which used to exist at CERN. And this is actually photograph of a flower bed, which in fact I used to see from my office at CERN. And this is the area of 10 meter by 10 meter. And in this, inside this square, you have these flowers. Okay, you have taken this picture. Now, supposing you zoom in this picture. We all zoom all the time when we are taking our camera and taking pictures. So now you zoom in such that you increase the resolution by a factor 10. What does that mean? That means that now when I zoomed in, the same area that I had here, which covered 100 meters, the same square now covers 1 meter by 1 meter. So I had zoomed in by a factor 10, and I begin to see the flowers. I begin to see leaves. I begin to see maybe there are some bees on the flowers. And actually, if you go down by another factor of 10, that means you zoom in from 1 meter by 1 meter to 0.1 meter by 0.1 meter. Okay, and now you have gone from 10 meters to 1 meters by a factor 10, 1 meter to 0.1 meter by another factor 10, and then you begin to see this B. Now you go down by another factor 10, you begin to see the head of this bee, and then you begin to see, oh my god, this bee has these eyes. So another factor 2, 10, you begin to see this becomes photograph, and so far you can actually take these photographs. Okay, so now you zoom in and you begin to see the photograph of the compound eye of the bee. So remember, from 10 meter by 10 meter, we have come down by how many orders of magnitude? 1, 2, 3, 4. Okay, and this is the compound eye. Now you go down by another factor of 10, and this compound eye when begins to see this filament. And when you look at this filament, now you can, so we have come down another factor of 10. Now we go down by another factor of 10, we begin to see the basis of this filament. Now these photographs are sometimes artist creations and sometimes photographs taken with some ultra fancy techniques. So now the box is, instead of being 10 meter by 10 meter, this area is 10 to the minus 5 meters by 10 to the minus 5 meters. Now you begin to see the filament. Now another factor of 10, you begin to see the sort of base of the filament, and another factor of 10, you begin to see the strands. And then you can now use electron microscopes and do a further photography. Here now it's no longer real photography. You reconstruct quite often the positions of the objects that you are seeing, and these strands are nothing but the DNA strands. And see what has happened. From this square is now, it used to be 10 meter by 10 meter, present area 10 meter by 10 meter. Now it's representing an area which is 10 to the minus 8 meters by 10 to the minus 8 meters. Now, this is where you go down by another factor of 100 on each side. And then you will see that these are made up of carbon atoms. And this carbon atom has a nucleus at the center and the electrons going around it. And now, if you zoom in by another 4 orders of magnitude, I told you the nucleus is 10,000 times smaller than an atom. And then now you begin to see this nucleus, and another factor of 10, you begin to see a proton, because a proton is 10 times smaller than a nucleus. And now inside this proton, so now the same 10 meters by 10 meters, by zooming down 15 or 16 times, by each time by a factor 10, the same area now is representing a proton with 3 quarks inside it. And that's it. We really don't have any, anywhere we are going further down. Where did this whole story begin? The story began in the second of 19th century when the electron was discovered, and that was the birth of particle physics, I would say. And what did, there were 2 things. Faraday, by measurements, had said that electricity comes in multiples of a basic unit. So experiments with cathode rays by Thomson and the discovery of the electron sort of happened because Thomson noticed that in the cathode rays, he was able to see particles with an E by M ratio, which was different from the hydrogen ion. And then he sort of made contact with this hypothesis by Faraday and said that this cathode ray beam that we are seeing is actually a collection of these electrons, the units of electricity. And this was the first elementary particle in 1897. So how was this discovered? Let us remember what the apparatus was. It was a cathode ray tube, and electrons were traveling from the one end to the other end. And what does the cathode ray tube do? It accelerates the electrons, which are emitted first by the hot filament, and then you use the potential difference between the anode and the cathode for the electrons to get accelerated. So this was the basic accelerator, if you wish. And this basic accelerator, the classic accelerator, was responsible for the discovery of the first fundamental particle, the electron. And let me tell you, the reason J.J. Thomson was able to actually discover his electron, he's shown here in this photograph. He won the Nobel Prize the year after it was almost discovered. And the reason he could discover it and others could not, because he had access to technology, a very high profile technology at that time, that is to create good vacuum. Because if the vacuum is not good, then the air inside would cause discharge, and one would not be able to make observations on the cathode rays traveling from the cathode to the anode. So you see already the role of technology, the role that technology plays and played in the discovery of this first fundamental particle. The next step actually came when Rutherford did the classic scattering experiments. And anybody who is interested in science, all of us, we study in the 10th grade or maybe in the 12th grade, Rutherford's classic experiment, where he had a beam of alpha particles, which was coming from a radioactive source and which hit a thin golden foil. And what you noticed, what he measured was the alpha particles, how they were scattered from this thin gold foil. And he detected his alpha particles by putting a zinc sulfide screen and looking at the scintillations that were caused by alpha particles on this zinc sulfide screen. So his beam was the alpha particles beam. His target was the thin gold foil, and his detector was this assembly of the zinc sulfide screen and microscope. And he was able to, his colleagues who were doing these experiments were able to move this assembly all over the room, because this was just a very small room. And then what they found is that most of the alpha particles went through undeflected through the thin gold foil, as though they were passing through pure space. But sometimes they rebonded. And in fact, you could, now you have to compare this with what was expected. If they pass through, then you know that atom is nothing but a lot of free space. But sometimes it comes back. That means that the thin gold foil consists of large regions of empty space, but sometimes, somewhere, there is something which is sitting, which reflects these alpha particles, deflects and repels these alpha particles with a great, through the large angle. And from this, Rutherford actually concluded that atom had a point-like nucleus, that is, the charge inside an atom was all concentrated at a very small point, and rest of the atom was just pure space. So this, what he found was that by comparing the angular distribution, that is the angles, different relative number of alpha particles which will be scattered at different angles, by observing the angular distribution of the scattered alpha particle, Rutherford was able to draw a conclusion about the distribution of the charges, because alpha particle is a charged particle and it would be repelled by other positive charges of the nucleus and attracted by the electrons in the atom. Okay, so that was the general idea. Now, this is sort of telling you how one can use high energy particles to see things. And higher the energy, shorter will be the wavelength of those particles, and better will be the resolution, which can resolve the distances from each other. Rutherford had used alpha particles to look inside the atom, and his alpha particles had the energy of million electron volts, where 1 electron volt is the energy that an electron gets when it falls to a potential difference of 1 volt. Now, they can be used to measure distances. You calculate from the 1 MeV alpha particle, you calculate what is its corresponding de Broglie wavelength, which all of us, again, physicists study in 10th or 12th when we start studying modern physics. What should not be anymore called modern physics, but what used to be called modern physics when we were young. And then you can calculate this wavelength, and that wavelength comes out to be about 1/100th of an angstrom. So therefore, this tells you that this tells you that the nucleus, which behaved like a point particle, definitely had a size smaller than the 100th of an angstrom. Okay, and that is how one can now understand this. So in general, whenever we want to see things, and how do we probe them with different objects? For example, if you want to look at galaxies, then you use the radio telescopes that I just now talked about. If you want to look at planets, actually just a telescope, and these days a handheld telescope would do. For example, right now there is a conjunction of the Jupiter and Saturn and one more planet, I forget, which you can actually see using a telescope. So this you use using telescope, which Galileo taught us. A dog which is a meter high or something, or maybe half a meter high, we can see it just by eye. To see a cell of a plant, a biological cell, and see the nucleus inside it, actually that is how the word nucleus arose in the context of atoms also. That can be seen through just a microscope. Now in a microscope, we know as we go on decreasing the wavelength, we increase the resolution of the microscope. But if you want to look at DNAs, which are way smaller than this plant cell, I already have given you an idea how small the DNA strands are. To see that, you actually need an electron microscope. And then if you want to look at atoms and nuclei, what you really need is in fact accelerators or electron microscopes. And this higher and higher energies are required to probe smaller and smaller distances. So sometimes we call elementary particle physics also as high energy physics. And this is the first step to understand why now the investigations in high energy particle physics sometimes need very high energies, and hence the sizes of the objects that need to produce those energies, experiments, kind of become rather large. So that is the point that I want to tell you, that when we want to measure the size of an object and we want to probe the dynamics of the objects which are smaller and smaller, we need higher and higher energies, and that's the name of the game. So, actually, I will there are a few things here which I'm going to skip, in fact, but I'm going to emphasize only on this, that in the history, sometimes some particles, when we tried to increase the energies, some particles sort of came unannounced to the party. That we didn't expect them in the cosmic ray experiments, we just found them. Whereas sometimes the new particles, new interactions, were actually predicted based on the knowledge available of the interaction which hold the constituents together at a particular level. And then experiments were done to see that, and in fact, that's how science progressed. So this is really what's happening. Now, if I look at, I made this small digression about sizes, but let me go back to this, that after the nucleus was found, Rutherford sort of split the atom and said there is a nucleus at the center. Then, in fact, how did we know that the nucleus was made up of nucleons? That actually was arrived at by, this is where the role that the theory plays, theoretical understanding plays, is important, by observing patterns in the properties of nuclei, and by finding that the masses of the different nuclei were actually close multiples of the mass of the hydrogen ion. Actually, people came to the conclusion that nucleus is made up of some more constituents, namely neutrons and protons, but you needed more energetic particles to unravel the secrets of the nucleus, and you needed nuclear reactions. And this is what, by the way, Rutherford always wanted to do. He said that it has long been my ambition to have available a copious supply of atoms and electrons which have energies transcending those of the alpha and the beta particles from the radioactive bodies. So Rutherford had realized that if you, because he was a great experimentalist and a great theorist, he had realized that the nuclei are made up of something more. And to understand that, he realized that we need more high energy particles than what were available from radioactive bodies. And in fact, there were two types of accelerators: natural accelerators, which were the cosmic rays, and India had actually a lot of contributions in the early days of cosmic ray physics. And even now, I think Indians are beginning once again enter the area of cosmic ray physics in a big way, and the man-made accelerators. So these are the cosmic accelerators. These are the cosmic rays which come from from the atmosphere. And in these cosmic rays, one found a whole lot of particles. And what were the energies of these cosmic rays? This is actually a big story, and I'm not going to go into that. But these are, because that is not the focus of my discussion. The cosmic rays are very good. They have very high energies, and they have, in fact, contributed very fundamentally in the discoveries of what lies within. However, these are not controlled experiments. We cannot control the original energy of the primary cosmic ray. We don't even know what it is. It just comes and does something for us. We study what has happened and we learn something from there. And this is actually, I produced a paper, cover of the paper, which was written by one of the cosmic ray physicists, M.G.K. Menon, in the early years of the cosmic ray physics. But this is just to show you that we used to do this. Indians used to be very active in cosmic ray physics. But I'm more interested in the cases where the energies actually could be controlled. And these increasing energies of the accelerators have actually revealed newer and newer substructures, and the field of accelerator physics and high energy physics, and therefore the theoretical particle physics, have got inexorably linked. And it is this link that I'm trying to sort of tell you the story about. So how do you accelerate particles? That is simple. You either accelerate them by running them through a potential difference, or the other thing is you try to use move them in a magnetic field in the circular orbits, and then you give them a kick at one point at the end of the circular orbit with the electric fields. And that is actually the kind of method that is used today. So this is the 1931. This is a Cockroft Walter generator accelerator, which was in fact built as per the exhortations from Rutherford. And this was built in the Cavendish laboratory. And this, as you can see, because they will be sparking, you had to use a lot of insulation. And this is inside a room. This accelerator was based and could accelerate electrons or the ions to energy of 1,000 million electron volts. And that was actually a big increase. However, at the same time, in 2 years, Lawrence and Livingston came up with this idea of accelerating electrons using the magnetic fields and electric fields together, and that is called the cyclotron. And this is only 4.5 inches in size. And here is a photograph of a quarter, American quarter, to tell you this was really indeed a very small size object, but it could accelerate to 1 million electron volts. This was a big achievement. And after that, the accelerators the story of the accelerators grew by leaps and bounds. And this is the energy of the accelerators kept on growing till in 2007, we have now reached 2012, we reached 10 to the 4 giga electron volts, or say 13 TeV. 1000 GeV is 1 TeV, 13 TeV energy at the Large Hadron Collider. So, but however, even today, the first stage of an accelerator is this Van de Graaff generator, and then you accelerate objects, transport them And then you use your tricks, various tricks, and use the electric and magnetic fields very imaginatively, and that's how these finally the LHC tunnel gets these protons, which are accelerated to an energy of 7,000 giga electron volts per beam. So this is how the energies have gone on increasing. Now I go back to our understanding. So, if you were living at Rutherford's time, the fundamental building blocks were perhaps only electrons and nuclei. But as Rutherford himself suspected, nuclei were not fundamental. And actually, by 1947, large number of newer particles, which were just like protons and neutrons and pions, were found. And these were found in these cosmic ray experiments. So this is the role that these cosmic ray experiments played. And as a result of which, one realized that neutron, protons, and electrons and photons cannot be the set of fundamental particles, and therefore one started thinking a bit more about it. And then around 1960, now this is where the data from the cosmic rays, one measured the lifetimes, the masses of all these particles, their interactions, and Gell-Mann and Zweig saw patterns in those properties, and in fact they put forward a quark model of protons, where they said that quark is, for example, made up of two up quarks and one down type of quark. Antiproton is made up of two anti-U quarks and one anti-D quarks, so on and so on and so forth. And this is what was postulated in 1960. But at this point, one saw that they gave a really order to this zoo of particles, but you couldn't break a proton or a neutron. I mean, if you heated an atom, the electrons came out. So you knew that the idea that the atom were made up of electron and nuclei was correct. When you bombarded one nucleus with another nucleus, you saw neutrons and protons coming out. So you knew that the idea that the protons and neutrons are inside the nucleus are correct. But now when you went on increasing the energy, because along with hand in hand went also the accelerator building, and people started doing experiments at the accelerators with protons or neutrons. And then one saw that one could not break protons and neutrons into something smaller. But Gell-Mann's idea said that they should be made up of something more smaller objects. Not only that, these smaller objects needed to have fraction of an electron's charge. So that all looked very, very odd. But what happened was 1964 onwards, the same time when Gell-Mann and Zweig put forward their idea, 1964 or so, there was an experiment which was at Stanford Linear Accelerator, and it was a 2-mile long accelerator where you had an accelerator which accelerated electrons, and these electrons hit a nucleus, and then you look at the scattered electron in the detector. Please look at the similarity with Rutherford experiment. Instead of the alpha particles, now you have electrons. Instead of the zinc foil, you have a nucleus. And instead of the detecting with a zinc sulfide screen, you had a pretty complicated detector. I will show you on the next slide. But the arrangement was accelerator, beam, incident on a target, look at the scattered beam, and detect the particles through a detector. And now this electron energy was about 400 to 600 MeV. If one calculated the wavelength of this electron energy, and electrons of this energy, one found that they could probe distances which are 1,000 to 10,000 times smaller than the Rutherford's alpha particle. So now what people did, they just counted the number of electrons which were coming out at a particular angle theta and compared it with the expectation if the nucleus was just a point particle. So that's what they did. But now you see Rutherford's experiment was fitting inside a room. This is this huge long accelerator, and there is this huge detector in a room at the end in this building. This is I don't know which one is the building. I have never been at SLAC accelerator. And here is a person standing here. So that tells you the big detector. This is called the spectrometer. So this spectrometer, being very complicated and heavy, could be moved only at few angles, unlike Rutherford's detector, which could be moved all around the room. But anyway, these measurements were made. And actually, these measurements told already that there exists inside a nucleus a proton and a neutron. And inside a proton, there exists some more fundamental objects, and further you could measure the properties of those objects and check that these properties were exactly the same as what were required by Gell-Mann's model. So lo and behold, the theoretically predicted quarks were actually seen in an experiment which was not quite designed to look for them. It was only designed to see if protons and neutrons or nuclei are made up of something more. These kind of experiments are called deep inelastic scattering experiments, and they were very famous, and they ruled the world of particle physics from 1964 till about 1992 and taught us a lot about what lies inside the matter. But actually, this higher energy was not only to look deeper inside the matter, but it was also because as time went along, the colliders and target machines, actually after the first discovery of the substructure, they did not find any further substructure. They kept on looking for it, and all they could see was results that were completely consistent with the assumption that the quarks and the electrons are fundamental. But now the higher energies did something else. These higher energies started finding newer and heavier particles and newer interactions that were predicted by these theories. And actually, these machines, the new accelerators, were built by doing calculations which were based on the results of the earlier machines and the theories that us theorists has constructed. But the higher energies and the precision measurements required bigger and more complex detectors, bigger and more complex accelerators. So how did the particle physicists knew which energy to go to? This is where the science and technology together join hands in deciding how we go on. In case of Rutherford, the energy was required that was decided by Gamow's theory of alpha decay, which predicted the height of the Coulomb barrier. So you knew how much energy you need to give so that your alpha particle will be able to come out of the nucleus. Many decades later, Glashow, Salam, and Weinberg's theory set the bar for the high energy physics machines so that they can produce the top quark, the W, the Z, and ultimately the Higgs boson. And the hand-in-hand development of theory and experiments to measure and detect and technology, this is very, very important. And that was an essential part of the development of high energy physics. So I'm almost coming to the end of my description of this mega project. And now this is what led to this immensely successful and immensely complicated instrument to build. This is the Large Hadron Collider, which is lying deep underneath the ground, and two proton beams collide head-on, 6.5 TeV, that is 6,500 GeV. And 1 GeV, remember, is 10 to the 9 electron volts. So this is 6,500 into 10 to the 9 EV. And there is this proton beam, two proton beams circulating against each other. And this is the first ring which accelerates the objects, then transfers them to the another ring. That's what I was trying to tell you, that this is a complex accelerator complex, in fact. And then these two rings intersect each other at 4 points where we keep detectors. And this is a typical collider experiment. So this squeezes energy into space about a million times smaller than a mosquito, and temperatures which are billion times higher than that at the center of the sun. And these energy densities and the temperatures that we have produced actually are very, very similar to those that existed immediately after the Big Bang. Now, how do you measure, what happens, how you detect the particles that are produced in these reactions? So now generally energy of particle is measured by radiation loss, and that is where you have to make calorimeters. But particles like muons do not lose energy very easily because they don't interact very easily. Because basically all the detections are based on electromagnetic interactions of the particles. So in the case of muon, the energy is measured using bending of tracks. But high energy of a muon means that it will bend very little, because remember, the bend radius of a object of the track is follows this particular relation, and B is fixed by technology and cost. Therefore, for a given B, if you have larger V, you need, as in faster muons, you need larger R, such that the size of the detector has to grow as we start doing experiments at these higher and higher energies. Mega sizes also mean mega expenses, also need, million different types of expertise. So no one person, no one laboratory, no one country can do this in self, and international collaborations are necessary. So I have tried to convey to you why now the experiments that are happening at the Large Hadron Collider require essentially have to be mega, and why they need international big collaboration. So I want to actually take the case of our Indian Neutrino Observatory next. So, neutrinos, they are actually the next frontier, apart from the Higgs boson discovery and the search for the dark matter at the collider, and search for Higgs physics, more accurate Higgs physics studies at the Large Hadron Collider. The next frontier in particle physics is one of the next frontiers is really neutrino physics. Now, where do neutrinos appear in nature? Neutrinos come out from sun, neutrinos come out in the Earth's crust, neutrinos are emitted by reactors, neutrinos come out at the particle accelerators, neutrinos come in the cosmic rays, neutrinos are emitted by astrophysical accelerators, that is by various objects, quasars and pulsars and what have you. Then cosmic Big Bang also has given rise to neutrinos in the everywhere around us. There are about 330 neutrinos per centimeter cube, and we have an indirect evidence for this. Supernovae emit neutrinos, and sun emits neutrinos. So these neutrinos come in all shapes, all sizes, all energies, in all different numbers. And they are there, they are large in numbers. So just to make a small calculation, about 65 million neutrinos pass through your thumbnail every second. So then why don't I feel it? I cannot feel it because they interact very feebly. So what we can call their mean free path is very, very large, and therefore we don't feel these neutrinos. But there is a lot of physics in how these neutrinos behave. But not only that they behave, so they are almost invisible in the detectors. That is the problem. And therefore, detecting neutrinos is kind of a waiting game. That is, even though there are 100 trillion neutrinos per second that are passing through a human body, if you would have one interaction in 100 years, and if you want to have, what you want to have is something like about 100 to 200 interactions per day, and for that you need to increase the size of your detector. And India has been part of this waiting game since long time ago, and many different things happen in these underground detectors and neutrino interactions. And what happens is that when we are trying to detect neutrinos, many other things are happening, and therefore to get rid of those unwanted things, you actually have to go deep underground. This means excavations, this means use of mines, and this was one of the first neutrino detector that India had built in the Kolar gold mine in 1965. Now, this is just to show you the current state-of-the-art neutrino detector, and that is Super Kamiokande, and that is 50 kiloton of water. Okay, and there are these photoelectric tubes, and this is the huge detector, and you have to navigate this detector sitting in a boat, as you can see this. And in spite of this huge size, it observes about 5 to 10 neutrinos per day. So this is where, with neutrino physics, you need a huge detector, you need a huge size, and that is why I showed you the Indian Neutrino Observatory is trying to build world's biggest electromagnet, when the whole stack of this RPC would be about 5-story high. And all these kinds of experiments require precision machining, precision positioning, and precision measurements. For example, the proton beams have to keep true to their path to much less than a micron in traveling over the 27 kilometers at the LHC, which means that the magnetic fields have to be very, very precise. In fact, India made the precision magnet positioning systems which would help the LHC achieve it, and this was done near Bengaluru. And not only that, World Wide Web was invented at CERN by particle physicists to do analysis of the data, and it has changed our lives forever. I'm talking to you today only because of the existence of internet. So this is where I want to tell you that technology So there are two things that I wanted to show, and I hope you have been convinced that fundamental physics now has reached a stage where it needs mega projects, and the mega projects need cutting edge technology. But sometimes the cutting edge technology that the mega projects develop can do percolate, and definitely percolate to the society at large, and indeed change the way society lives. For example, artificial intelligence, for example, machine learning. Many of these things have been developed by scientists to analyze the multitude of data, and now it is slowly going to change. We perhaps look at our society, the way we invent new materials, so on and so forth. I just wanted to give one slide to give an idea why the detectors at the colliders have to be big and complex. That, for example, at the Large Hadron Collider, many different processes happen, okay, at different rates. And on the y-axis, you are here on the right-hand side, are the number of events that will happen for a certain in a certain amount of time. And what people were interested was looking at a Higgs, and with a mass of say 150 GeV. Then at the LHC energy, with a Higgs event would have happened at 10 to the between 10 to the minus 2 and 10 to the minus 1 level, whereas many other processes were happening orders of magnitude bigger than this, which means that you need to collide many more particles, and then you need to look at a needle in the haystack, and that's why you need complex and big detectors. Just to give an idea of the numbers that are involved, experiments measured 100 events of the type where the Higgs was seen through the production of 2 high energy photons, okay, and 10 events of the time when it was seen through production of 4 muons. And for every Higgs event, this is the Higgs discovery 10 years ago, which produced 2 photons, there were 1,000 million or 100 crores of events where other things were produced. So you have to pick up this one event out of the 100 crore events, and that tells you how big is the haystack and how small is the needle. And this is where you need to make measurements of energies and the momenta of the particles very accurately. Now I want to end with this, that LHC has also been a telescope in time, and LHC is able to recreate the conditions that existed in the universe here at 10 to the minus 10 seconds after the Big Bang. And in fact, what happens is that the standard model cosmology description of the early universe says that there is a hot radiation dominated plasma, which is almost an ideal gas, and this has been verified to the temperature of about MeV. The cosmic microwave background radiation really came from that era, and that is what we have measured. So we know this is true. But if we want to look at what happened before that, that is where Large Hadron Collider is required, and Large Hadron Collider will actually create 1 billion mini Big Bangs at the LHC every second, and thus the adventure of fundamental physics goes on beyond what particle physics did. And I have already discussed this with you, that the laws of physics which can explain the behavior of matter inside, the same laws of physics that we discovered at the heart of the matter can explain behavior of matter of all shapes and sizes. And that is where the knowledge of the physics at the small distance scale is necessary to explain what happened. Why do we exist? Or why does universe contain more matter than antimatter? Why does most of the matter in the universe does not shine? Why is the universe accelerating? So this interplay of the physics at the micro and the macro scale drives the understanding of the physics at the heart of the matter further. I don't have time, so I'm not going to show you the video that how big is the big. But again, we can go like the factors of 10 from inside a room to the galaxies and to the edge of the universe. And again, one can see that one needs to have orders and orders of magnitude. Every time by a factor 10, we have to go above. So now collider physicists are thinking of something called the International Linear Collider. And let's hope that someday that becomes a reality. And this is where we are. Possibilities exist that the particle theories will provide answers to cosmological questions, which I already outlined, and the high precision cosmological measurements perhaps can constrain particle theories. That is why what the LIGO will do, what the square kilometer array will do, what it will look at the center of the galaxies, at the edge of the universe, also has implications for what we understand about theories of particle physics. So clearly, very, very exciting times ahead. We are going to probe the universe in the coming decades through many different probes, to the optical, where India has the Hanley telescope, to the radio, where India is already has GMRT, and we are thinking of getting involved in SKA, I told you, gravitational wavelength, that is LIGO, neutrinos, where India has the Indian Neutrino Observatory, and Indians will also be participating to some extent in June, and the colliders, which are Large Hadron Collider and Indian International Linear Collider. I leave you with this picture of CERN through the photons as well as through the neutrinos to show you that indeed the multi-wavelength astronomy has become a reality already. So it's hopefully some of the guys, young guys and gals who are in the audience, I hope they are there, they will answer many of these questions, and the science discoveries that are made in these mega projects and the technological developments that happen during their execution are surely going to show us the way. Thank you very much for your patience and attention.
Thank you, Rohini, for this really, really fascinating talk. So, are there questions or comments?
Doesn't look like that, huh?
Okay, so maybe then I can start with a question, which of course is probably a very naive question, but for the sake of the young people, hopefully they are there in the YouTube link. How do you know that really the quarks are the ultimate theoretically? Is there a limit that we can put that
Yeah.
are the ultimate limit? Because we have these very big colliders and machines to really detect them, and maybe with an advanced technology which we can't see today will be seen tomorrow, but theoretically there must be a limit put to it.
Now, that is actually the point. In fact, this limit of 10 to the minus 18 meters that has been got is already the limit that we can get from the current colliders. Current machines cannot go beyond that. But right now, the fact that we say electrons or quarks are fundamental or elementary is not because we do not see any evidence for the structure, but it is because of the fact that we do calculations assuming that electrons and quarks are fundamental. And the calculations are very high precision calculations. And those calculations assume that the electrons and quarks are completely elementary. They use rules of quantum field theory. Very complicated ideas have to go in that calculation. And you calculate, for example, the correction to the gyromagnetic ratio of the muon using this theory. And now this has been calculated to 11 decimal places or 10 decimal places, and it has been measured to 11 decimal places, and the two agree. So this tells you indirectly that because here you have assumed that the electrons and quarks are fundamental to the highest imaginable energy scale. You have integrated over the momenta of these objects over all possible momenta scale. So this is a theoretical tool which tells you that what you have, if there was a substructure to the electrons, we would have seen already the evidence as a disagreement between the theoretical calculation and the measurement. So it goes beyond. So that is why I try to emphasize that it is the interplay between theory and measurements. Just by blindly making bigger and bigger accelerators, we are not going to learn much. That is part of the game of story of this game, that you need to know what you are looking for, and the direction from theory is very, very important. This is quite an unusual game compared to the usual way, the way we have been taught and thought about doing experiments. So this is a very special sort of experiments that need to be done.
Thank you. Thank you. I just thought that these few words probably will put some more clarification to the questions the young mind had.
Yes, thank you for that.
Are there any further questions or comments? That doesn't seem to be the case. I don't see. Also, there is no chat possibility. In these Teams, I don't see how to make chat because I tried to do something and it didn't work really.
Yeah,
So
it didn't work also. I don't see, I'm not able to see chat
yes,
anymore. Yeah.
exactly. So, Professor Ray, would you like to add a few words, the final comments from your end?
Yeah, I would like to thank Professor Gatbolli only for an excellent lecture, and particularly on a Sunday evening, and agreeing to give a lecture on the occasion of the National Science Day of SNBNCBS Center. I know you have been involved from the very beginning, and I remember meeting you about 2 years back in a evaluation of the this thing of all the autonomous institute of the DST. I remember interacting with you.
That's
So
right.
thank you very much. Thank you very much, and definitely you should visit us whenever is possible in the near future. That would be
That's right.
wonderful.
Okay.
Thank
Thank you very much for inviting me,
you.
and all the best wishes on Science Day to all of us.
Thank
Same
you so
here, same here.
Okay.
All the best wishes to everybody for this Science Day. And thank
Okay. Bye bye.
you and goodbye. Thank you.
Goodbye. Take care and see you
Thank
sometime.
you. Yes.
Sometime. See you
Some,
sometime.
much. Okay.
let's hope.
Bye bye.
Bye
Bye bye.
bye.
Bye bye.